microphones, please.
Okay, so good morning, and thanks a lot for this opportunity to speak to you about LISA. LISA is the Laser Interferometer Space Antenna. It's an orbiting observatory for gravitational waves in the 20 microhertz to roughly 1 hertz band. It's been selected by the European Space Agency to be the third Cosmic Vision large mission, which is slated for a launch in 2034. If everything goes well, we will have, let's say, a couple years before we start measuring, giving you science data, and hopefully this will be a 10-year mission. So LISA represents a very vast science and a wide range of experimental techniques to get it working. It's a big project. Right now we have roughly 1,000 LISA consortium members, representing something like 200 full-time equivalent workers. So I will give a talk which is just summarizing some of the work being done by these people in addition to the agencies and industry. We've had a very well participated LISA session this week, which has 2 more events this afternoon. I invite you to participate. So my talk will talk about what is LISA and what we will observe, so something about the LISA science. We had a spectacular talk yesterday by Elena Maria Rossi, and I'll just hit some of the high points of this. How does LISA work? I'll talk about the measurement concept and what are the main sensitivity limits. What have we demonstrated? And this is mostly coming from the LISA Pathfinder mission, which is interferometric tracking of free-falling test masses. And what are we still working on? And a lot of this is related to the fact that now we're going to have free-falling observers in satellites which are 2.5 million kilometers apart. And how do we make that long interferometry measurement? And how do we do this? How do we do the data analysis to pull out the many scientific sources in a very signal-dominated data series? So I'll borrow some terminology from our consortium coordinator, Martin Hewitson. The antenna in the LISA Interferometer Space Antenna is a constellation of free-falling test masses. These test masses are located free-falling inside spacecraft, which are at the 3 corners of a roughly equilateral, freely orbiting configuration. Our receiver is the laser interferometry technique. So the idea is that our antenna feels the tidal deformation, the tidal acceleration from a passing gravitational wave, and our laser interferometer receiver observes this in the modulation of the Doppler shift of light exchange between these free-falling observers. The low frequency limit of this is stray deformations of our antenna, stray tidal deformations due to stray forces acting on our test particles. The high frequency limit is the interferometer measurement fluctuations coming from shot noise and other optical effects. I think this is relatively similar to the ground-based interferometry. The ground-based interferometry, I think you can look at the antenna receiver system from the talks we've heard also as a single quantum optical mechanical system. In LISA, these 2 aspects are relatively separated because we're in a very weak light limit. So what are the characteristics of LISA? LISA has 3 arms along which we will exchange light. These are 6 one-way link measurements. And the arm length, or the separation between our free-falling test masses, is 2.5 million kilometers. This is roughly optimized for observing roughly 1 million solar mass black hole mergers in the millihertz regime, which is also the frequencies at which we will be doing a survey of binary ultra-compact objects in our galaxy. If you go to much longer wavelengths, you start being, you have so little light that it becomes difficult to phase lock your lasers. You also become more and more sensitive. The orbital stability is compromised over time by other objects in the solar system like the Earth. So in LISA, we have free-falling test masses. There's no suspension to get to the millihertz frequency range. You have to get away from the Earth, and you have to get away from mechanical or other types of suspension of the test masses. The orbital tidal accelerations on the LISA constellation are of order a few micrometers per second squared. The gravitational wave tidal accelerations are femtometers per second squared. So there's 9 orders of magnitude difference. We cannot compensate the micrometer per second squared accelerations without introducing noise, which would compromise our ability to measure the femtometers. So this is, this is an open loop interferometer. LIGO is locked on a fringe. Our fringes are flying by at 10 million per second, 10 megahertz fringe rates, because of the just orbital velocities, relative velocities between the different spacecraft are of order 10 meters per second. Our spacecraft are drag-free control. It turns out a spacecraft in orbit is not a good enough reference of geodesic motion, so we have test masses inside these spacecraft, which are our true end mirrors. It's a very unequal arm interferometer. This is just because of orbital dynamics, of order tens of thousands of kilometers difference, so of order 1% difference. And this is a problem for frequency, laser frequency noise, which would cancel out in a perfect Michelson equal arm interferometer. Finally, it's a very weak light system with something like 100 picowatts received power. This means that we can't just reflect the light back and forth like you do on the ground. You have a single arm transponder configuration where light is measured, it's phase locked and sent back. The other thing that's different from ground-based interferometers, there's no combination, no direct combination or interference of light between adjacent arms. We make all these single arm measurements. I should stress also that in some previously studied versions, there were only 2 operating arms. Having 3 arms allows us 2 different Michelson combinations, which are semi-independent, which give us a full polarization of the gravitational wave. It also gives us an important experimental discriminator. There's also a 3rd combination, which could be classified as a Sagnac variable, which is basically very insensitive to gravitational waves, which is a probe of our measurement noise. So this is an ESA-led mission, European Space Agency-led mission. That means that ESA supplies the spacecraft, which are 3, and some possible key payload items, which I'll note in a moment. They're responsible for the full mission performance, the mission and science operations, responsible for the launch, the communications, the transfer. While this is similar to what LISA might look like in the end, these are really sort of notional views of what the hardware might look like. This is coming from an ESA internal study. This is currently being studied in detail in industry. It's actually a competitive study, so I won't be showing any more updated images of the satellite. But this is similar to what we will launch in that you have 2 telescopes in each of 3 spacecraft, and these are looking to the distant spacecraft. So ESA supplies the overall mission lead and the spacecraft, certainly, among other things. It's up to a consortium of European member states and international partners to provide most of the measurement apparatus. Most of this is what we call the MOSA, the moving optical subassembly, and there are 2 of these for each of the 3 spacecraft. This is comprised of a telescope, an optical bench, and this is the optical metrology system, and this is designed for measuring interferometric measuring to the distant spacecraft and to a test mass, which is part of this gravitational reference system, a free-falling test mass. So this consortium, I've put flags, which are the probable providers of the different hardware for the mission. This consortium is also a science consortium, which is tasked with assisting the European Space Agency in producing all the science of LISA. So what will we see? LISA is a high-resolution deep universe observatory. We heard some fascinating talks about current ground-based astronomy and ground-based gravitational wave astronomy and where it's headed. Most of the LIGO sources are seen at redshifts now of 0.1, 0.2, 0.3, with signal-to-noise of order 10s. This was described in Lisa Barzotti's spectacular talk the other day. LISA, our typical sources, or some of our favorite sources, are million solar mass mergers. We can see these, the typical distances we'll see these are out to redshifts of several, and these will be observed if LIFA is working properly with a signal noise of up around 1,000. At lower signal to noise, we hope to be able to see even farther out to what we call the cosmic dawn, when the first stars and galaxies were formed, and where we might see the seeds of these around 1,000 solar mass or 10,000 solar mass out to redshifts of 10 or 15. So this is high resolution, it's deep universe. It's also a low frequency observatory. This is one of our most massive sources. two 5 million solar mass black holes merging at z equals 2. You can see that the highest frequency at which we could hope to see the gravitational radiation from this is around 1 millihertz. So this is a very low frequency source with a signal to noise of 1,000. You can see that in the last day, we're building up most of the signal to noise ratio, and this is so for frequencies above 100 megahertz. As you go to lower frequencies, this comes into our band for something like a week. If you go to slightly less massive mergers, the frequencies get pushed up a little bit and the timing band goes down. The timing band increases as well. But you can see that the low frequencies are very important for extending our observation time, which is also important for having some warning that one of these coalescences is happening, so we can look for a possible electromagnetic counterpart. So these are all frequencies, these millihertz frequencies and below are all frequencies where we're limited by the stray forces acting on the test masses. So the message is we need to get that right to have the full LISA sensitivity. I said before our million solar mass mergers are seen with SNR up to 1,000 at Z of several. We should be able to see these in all of the universe, which is, we should see these out to distances, any relevant distance for which the universe is old enough to have made these sources. These sources exist. We don't know how they were built or how they came together from different mergers. We hope to trace this merger history back all the way back to order 1,000 solar masses, and seeing these out to, as I said before, the cosmic dawn from Z to 10 equals 10 to 15. We also should be able to see compact, black holes from stellar object residuals around 100 solar masses. So with these very high resolution observations, we get sky positions below a degree for the brighter sources. We should get high precision measurements of mass and luminosity, the visibility for the most massive sources of days, for the lower mass sources to years in our data. There's a possibility of multi-messenger astronomy with electromagnetic counterparts, and so this will be a rich data set, a real survey from which we can do galaxy formation studies, also cosmology with standard sirens, and many tests of fundamental physics. If you combine, I neglected to mention that I was comparing earlier with ground-based astronomy in the current moment. By the time LISA is flying, there will be, I believe it's called the third generation of the ground-based detectors. And between LISA and these ground-based detectors, we should basically cover the whole spectrum of black hole mergers, including, this is the Einstein telescope, predictions for high resolution signal to noise out to large redshifts. And so LISA and the ground-based observation campaigns will be teaming to study black hole mergers across a whole range of mass values and be able to investigate a whole range of formation scenarios. The first LIGO source, we were very excited for many reasons, but among these, for those of us in the LISA community, is that we would have seen the very first one with a signal to noise of the order of 5 to 10, not very high signal to noise, and something like 5 to 10 years before the merger. So multi-band observation is possible between LISA and the ground-based detectors. We don't think this is typical. It turns out that the best source so far for multi-band was the first one. However, LISA will see many, so dozens to 100 stellar black hole binary coalescences at frequencies, or at merger times, which are maybe tens of years, and it offers some complementarity to ground-based observations because you're sensitive to when there was maybe a larger eccentricity, so you learn something about the environment in which these were formed. I won't get into this. There'll be a talk this afternoon by Paul McNamara. This is electromagnetic counterpart searches for massive black hole mergers with Athena. So LISA and Athena, we will have an overlapping observation time. LISA cannot be pointed. LISA will over time, over the weeks before a merger, narrow the error box on the sky position, and as it does so, Athena can slew and look to examine for an electromagnetic counterpart. Finally, and certainly last but not least, EASY will provide an exhaustive survey of compact objects, mostly white dwarf binaries in our galaxy. It's believed that something like 10,000 of these will be observable, individually resolvable in our first year of data. It's believed that there are millions of these which will form a cofusion limit at millihertz frequencies. Of these resolvable ones, there are 11 that we know today, which have been found optically and have a signal to noise of more than 20. So we should have very high precision measurements of these objects. We also believe that hundreds of these, of order 100 of these, will be discovered and can then be observed in the Gaia and LSST data sets. So finally, we heard a wonderful talk the other day about images of stars orbiting around the center of center of our galaxy and the black hole at the center. These were done with stars which have orbits of, I believe, light days. It would be nice to do this experiment with test particles orbiting around a massive black hole much closer to the event horizon, so with periods of order light minutes. And this is what we hope to do with what are called extreme mass ratio in-spirals, or EMRIs. These are stellar mass black holes orbiting around supermassive black holes and allowing a number of tests of general relativity close to the event horizon, including precession of the orbit, precession of the orbital plane. So there's a lot of fundamental physics. Our task then experimentally is to provide the resolution that we could see the tidal deformation produced billions of light years away by this stellar mass object orbiting around a black hole. So how does LISA work? This is relatively simplified, but we think of this as a time-shifted Doppler gravity gradiometer. So our experiment, you can imagine one free-falling observer sending out a laser beam with a certain frequency towards the second one. The second observer receives this laser beam and produces a phase-locked or phase-coherent copy of it and sends it back. So you can think of this basically like reflecting back, except that we don't have enough light to just have a simple reflection, but you can think of this as reflecting back. And then O1, the observer 1, interferes this returning beam with his local beam, his or her local beam in that moment. And you measure what's called beat frequency, the difference in frequency between these two beams. So this is the basic laser measurement. I'm simplifying. It doesn't have to be done in this closed loop fashion, but it will be done as such. And these will make this measurement along 3 arms. If you calculate what's the time derivative of this beat frequency, this encodes the gravitational wave strain. Maybe it's familiar, this is expressed in terms of the frequency derivative, which is similar to an acceleration. If you integrate this twice, you get the standard formula for the phase accumulated in an arm of a gravitational wave detector. So this gravitational wave strain is then in direct competition with the stray acceleration differences, time shifted, acting on the two observers. It's also in competition with our measurement, our ability to measure the phase of the light here and here. And it's in correct competition with the laser frequency noise. In fact, if you think of, in the absence of these other things, I'm just measuring the laser frequency at this moment, minus the laser frequency it had a 2-way light time ago. And it turns out that this is our first big enemy and our first big noise source that we have to cure. So the way we do this is actually a little bit different. So the observers are actually a composite observer, and what we wind up measuring, because the spacecraft isn't geodesic enough, we have a free-falling reference test mass, so we have to measure from test mass to satellite, from satellite to distant satellite, and from satellite to test mass. And so there's 2 interferometers here. There's also a third interferometer on board, which is to basically compare the frequency of light in this arm with the frequency of light in the light source for the other arm, which is basically, you can think of this as performing the role of like a beam splitter. So at low frequencies, we're limited by our test mass acceleration. It needs to be at the 3 femtometers per second squared level, so sub-femto g. At high frequencies, we're limited by the interferometer readout noise, which is something like 10 picometers per root hertz. Then as we get to higher frequencies, we pay a price when the wavelength of the gravitational wave becomes smaller than this separation between the spacecraft. So the key to the low frequency sensitivity is the precision to which the test masses are in free fall and pure geodetic motion along time scales of 20 minutes to hours. So this is very difficult to test on the ground. We dedicated a mission called the LISA Pathfinder, the Einstein Geodesic Explorer, to measuring these, trying to measure the stray accelerations on the test mass. We did this by shrinking an arm of LISA into a single spacecraft, and we're measuring differential acceleration. In so doing, we're testing a number of things. We're testing the free-falling test mass. We're testing the gravitational reference sensor, which is an electrostatic sensor and actuator surrounding the test mass. We're also testing our ability to track these with an interferometer with very high precision. We're testing the drag-free control of satellites, so our ability to control a satellite around the test masses. We also tested a number of items which I will list shortly, but the spacecraft gravitational balancing, the test mass charging, the environment we have in space, and magnetism, and thermal, and many other things. So this is LISA Pathfinder. It's two test masses with a 38 centimeter separation. These are heavy test masses, gold platinum, roughly 2 kilos each. They're cubic test masses. And you measure their differential acceleration with a high precision interferometer. So the test masses are inside a vacuum housing, which is vented to space to have the nice vacuum of space and not the dirty vacuum of the spacecraft. They had to be caged during launch so that they didn't break apart. We have to discharge them periodically or continuously with UV light to neutralize cosmic ray charging. So in trying to do LISA Pathfinder, our heritage was from geodesy missions like Goche and Grace, which had achieved pico-G per root hertz free fall. Okay, this is around the Earth. This is what you need to start seeing the gravity gradients and their time and spatial evolution on the Earth. But we need to make a jump of roughly 4 or 5 orders of magnitude. So why can we do this? The first thing is really location. With geodesy in Earth orbit, you have a big gravity gradient of order micrometers per second squared between the two test masses. We sent LISA Pathfinder to the Lagrange point, where the Earth's gradient is many orders of magnitude below our threshold, and what we see is actually the local gradient from the spacecraft itself. So what were we testing? And this, you know that if you have to keep the two test masses inside the same spacecraft, you basically have to compensate this gradient. If you have to compensate micrometers per second squared, you're going to have fluctuations in the forces. And so this is a limiting factor for a measurement performed in low Earth orbit. Going far away, we knew that this noise source would get much lower. What we didn't know, and why we had to do this test, are the surface forces, so any unmodeled forces acting on the test mass, are they small enough to allow this jump? And so the design philosophy was to use heavy test masses with gold platinum, magnetically pure, with big gaps around the test masses, several millimeters. We tested this as well as we could on the ground. We did this with a torsion pendulum. We got maybe to within about a factor of a few, worse than our Pathfinder goal. However, this wasn't a fully representative test, and we needed this flight test to convince us that this worked. So in Pathfinder, as I said before, you have to force one test mass to follow the other. If there are two test masses inside the same spacecraft, the spacecraft can't follow both of them. So the spacecraft follows test mass 1, and you force test mass 2 to follow test mass 1. And basically your science signal is how much force do I have to apply to test mass 2 to keep it at the same distance, keep it moving with the same acceleration as test mass 1. And the noise in that force that I'm applying is the noise I'm compensating all the stray forces acting on it. This way I can quantify them. So as we settle down into our drag-free operation in the finest science mode of measurement, we can write down this delta G, which is the difference in force per unit mass. I see My graphic has gotten mangled a little bit. And this is basically just the acceleration that we measure minus the force per unit mass that we're applying. And if you read this axis here, these are 50 picometers per second squared. Turns out this is about 20 times smaller, about 10 to 20 times smaller than our goal for this. This is indicative of how well we balanced the gravity on board the spacecraft so that this differential acceleration was as close to zero as possible. So when we saw this data, this was very good news. So our goal for Pathfinder is this pink curve. Our pre-flight model was this, that at low frequencies we'd be limited by actuation, having to balance this differential force. At middle frequencies we'd be limited by Brownian motion of the test masses. And this is from residual gas impacts, residual gas molecular impacts on the test mass. And at high frequencies we'd be limited by our interferometer readout. As we started measuring the first day of the mission, this is, I don't want to say just turning it on and it worked, but after our first day of science measurement, this was our result. As we kept measuring, these are our first published results, and this is basically our final result here. So over time, our measurements are getting quite a bit better. We think we understand all of this. So at low frequencies, we're limited by the actuation noise, and with this fine gravitational balancing, we could basically limit the amplitude of the electrostatic forces we're applying to the test mass. At middle frequencies, middle for us means millihertz, the pressure, the gas pressure around the test masses is going down. This is in a vacuum chamber which was vented to space after we reached orbit, and so in the year following that, the pressure dropped by about a factor 20. Finally, at high frequencies, we were limited by the interferometer, and we made some corrections for some cross-coupling to the spacecraft motion. So I'll give just a few details on this in just a moment. This is our final result. So our final result, this is our goal for LISA. This is what we based our proposal for the LISA mission on. The blue curve here is, and you see some error bars, blue curve is our experimental result. So we're basically proposing a mission that that we have achieved this test mass acceleration noise below this level at all frequencies. We extended this down to 20 microhertz. The original goal of the mission was a millihertz, but there was nothing limiting us to measuring longer, and this is important for the supermassive black hole science, so we're able to publish results down to these very low frequencies. Okay, so this is the good news. Actually, for LISA, we don't have to do anything better than what we've done on flight already. So we spent most of the mission then trying to understand every conceivable noise source, both for acceleration noise and also aspects of the interferometer. And if we add up all our noise sources, and the biggest ones are the interferometer at high frequencies, the Brownian noise at middle frequencies, and this actuation noise at lower frequencies, you get this black curve. So this is one skeleton in our closet. I guess all all experiments, certainly small force experiments, are limited at low frequencies, typically by what they call mystery noise. This was mentioned in LIGO presentations as well. We explain something like half the noise power of our noise at the lowest frequencies. And so when we're designing and you say, all I have to do is repeat what I did, this is an active challenge for us to appropriately set all the requirements which guarantee that we will get the same thing in LISA. So just very quickly going through some of the things that we demonstrated with LISA. With LISA, we demonstrated very high performance interferometer. What we needed was 10 picometers per root hertz. What we got was about almost a factor 100 better, around 35 femtometers per root hertz. At all frequencies below about 30 millihertz, what we're seeing is real test mass motion, so we're not seeing the interferometer noise. Only at high frequencies can you see this, and it was extremely well performing. This is a demonstration of a local interferometer, which is one of the things we need for LISA. Brownian noise at the beginning of the mission, if you calculate our noise floor at middle frequencies, it corresponded to a residual gas pressure, something like 20 micropascals. Over time, this noise fell. It continued to fall, falling below this green line, which is our LISA spec. At the very end of the mission, we dropped the temperature of the satellite another 10 degrees. So at room temperature, a Okay, room temperature, something like 10 degrees means a factor 2 in water outgassing. And so this is consistent with having something like a micropascal of water at the end of the mission. This is acceptable for LISA. I said we did gravitational balancing. We need this for LISA as well. In LISA, we want to balance the G, the little G felt by the two test masses, to something like 500 picometers per second squared. We achieved this, or roughly this, on all 3 degrees of freedom on LISA Pathfinder. I won't get into the details of this. Our big noise source going into the mission was actuation noise. It turns out it wasn't dominant. It wasn't dominant because we got the gravitational balancing so well. We could see the actuation noise only by increasing the size of the forces we were applying. We understand this. We think this is well modeled. This is also another key aspect for LISA. And just one final, another thing I'll mention regarding the test masses, they charge up with cosmic ray charging. This random cosmic ray charging produces a random charge on the test mass, which in the presence of any electrostatic field will cause a stray acceleration. We were able to measure this, and it turns out that you have something like a shot noise corresponding to something like 1,000 charging events per second. And this is consistent with LISA. This is something which we had to go to space to measure. We also showed that you can control a spacecraft. So we need to control the spacecraft by something like nanometers, so that it moves around the test masses with a very limited motion. We were able to do this. We use cold gas thrusters, and we intend to use these also for LISA. So what's left? Okay, what's left after LISA Pathfinder? And I'll just show a few slides to illustrate this and give you some idea of what we're working on now. But the simple answer is that we haven't demonstrated the long-arm interferometer, the inter-spacecraft interferometer, and LISA will also have a signal-dominated data set, which is very different from what we have now in ground-based astronomy. I could just illustrate this in the following way. This is again viewing this as a differential acceleration measurement. This is the tidal acceleration signal, a few hundred femtometers per second squared, produced by a 500,000 solar mass merger. If I superimpose real measurement noise, this is our test mass acceleration noise from LISA on top of this, from LISA Pathfinder, what we measure in LISA Pathfinder, you can see that this basically doesn't change the picture. So even in the presence of low frequency acceleration noise of the test masses, we have a huge signal to noise every cycle, okay? This is a zoom of this. You can see maybe there is some noise in the green signal. So there's a couple caveats to this that I need to present. So the first is that on LISA, we are photon starved. We only have 100 picowatts of light power, whereas in Pathfinder we have milliwatts. So this will give us noise, at least at the higher frequencies. It looks more something like this. The other thing in LISA is we have millions of white dwarf binaries from our own galaxy. And if you simulate the effect on this measurement that they have, you can see that this is making, this changes the picture also. Finally, okay, so this is assuming I'm neglecting laser frequency noise here. Okay, and so if I do just, so we know that in a Michelson interferometer, you can cancel out laser noise if the two arms are equal. Our two arms are not equal, but if I add in a second arm and just combine and make a Michelson combination of the data, our data look like this. And if I zoom out, you see that we've gone to over nanometers per second squared accelerations instead of the femtometers per second squared accelerations. So this is our biggest problem, and I'll try to explain this and how we would deal with this in LISA. Okay, so I've mentioned this before. It's a weak light interferometer. You launch a 2-watt beam. The beam is 30 kilometers across, something like this, at the other distant spacecraft. You collect something like 1 photon every 10 to the 10. Okay, and so we have to do a very weak light interferometer. Additionally, our orbiting triangle is not perfectly rigid. Okay, so it has motion just due to Keplerian orbits. This means that the arm lengths are different by up to tens of thousands of kilometers. There's relative velocities of 10 meters per second. This is why we have our interferometer signal is at the megahertz frequencies. And you have the breathing. The angles are not exactly 60 degrees, so our telescopes have to articulate. If we look at the frequency issue, so the frequency will couple in to, so the frequency noise of the laser couples in to our interferometer through this delta L, which is the difference in arm length. Okay, so we have a total budget for optical measurement of something like 10 picometers per root hertz. If I put in the simple data for how stable our lasers are after cavity stabilization, how different are the arms, you wind up seeing that you get micrometers instead of 10 picometers. So the way we deal with this is something called time delay interferometer. So you can imagine what we do so all our measurements are beat notes made along a single arm. If I subtract the beat note from this arm minus the beat note from this arm, that's a simple Michelson combination. Now what we do is we subtract from this, we basically take essentially a time derivative regarding most of our noise sources. This is just like taking a time derivative. What we do is we subtract off these two beat measurements, the difference in the beat measurements, at slightly different time. For arm B, we subtract this off at a time, the two-way light travel time for arm A, and we subtract off for A at a time which has been retarded by the two-way travel time along arm B. And what happens here is that basically we're comparing the path of a photon which was emitted, photons which were emitted at the same moment and were measured at the same moment at the end. So we've basically synthesized an equal arm interferometer. For most of our noise sources and the gravitational waves, this is sort of like applying a high-pass filter to our data. It turns out if you do this at just the right travel times, you're canceling out the laser noise. And so to do this, though, you need to know these distances. You're essentially synthesizing an equal arm interferometer at 1 meter. And so you have to do this with nanosecond timing, and this is done by arranging tone on the laser. It turns out this is exact when the arm lengths are different, but they're completely static. When you have a rotating and flexing interferometer, it turns out you need to do yet another round trip around this to cancel out the effects of the acceleration. This is called second generation TDI. So if I look at the frequency noise problem in LISA, at the top you see the one-way frequency noise. If you look at the round trip frequency noise, you've already lessened this. If you look at the simple Michelson combination, you're about 7 orders of magnitude beyond what we need to do. And this is all done with TDI, time delay interferometry. So a couple important steps experimentally have been made very recently. One of these is at Albert Einstein Institute. So you have microhertz frequency modulations coming from the gravitational wave. This is on top of 10 megahertz Doppler shifts, and it's on top of 30 hertz frequency noise. So you need a very high fidelity phase measurement. This is recently with order 10 to 11 dynamic range. This has been demonstrated on the ground with a fancy null test. This was presented at this conference. The other thing is now we have measurements from the GRACE geodesy mission, which will be published shortly. There's been some talks at this conference, which have demonstrated laser interferometry between distant spacecraft about 200 kilometers apart. These have demonstrated 100 picometer type noise. This has a lot of things in common with LISA in terms of frequency noise, weak light interferometry, high Doppler shifts. So this is very important benchmark for us. So finally, just a couple things which are new in LISA that we're working on. So this is a notional version of the LISA spacecraft with 2 test masses. You need to measure test mass to test mass with picometer resolution. The spacecraft is moving with nanometer resolution. So it means that when you're combining these measurements of the local interferometer and the long interferometer, this has to be done with high precision. We also have issues that the spacecraft is not just translationally noisy, it's also rotationally noisy. And this inserts something called tilt-to-length coupling, which is, you could think of an imperfect alignment between your local interferometer to the test mass and your long interferometer to the distant spacecraft. And there's also gravitational forces which are rotating with the spacecraft that we have to deal with. And okay, I won't go into this, but basically we count on having intrinsically high fidelity interferometry measurements to have a common mode rejection of the spacecraft motion. We also need to do a subtraction based on an in-flight calibration for this, this rotational motion of the satellite. Just a couple other final issues. In Pathfinder, one of our other skeletons in the closet were a population maybe of over 1 per day. There was a nice talk on this by Eleonora Castelli, of glitches. So these were impulse-like forces lasting tens of seconds, as if they were a force acting on one test mass. Okay, so if for the Pathfinder data, these were fairly rare, we could fit them out and analyze the residual data. You could fit them out in LISA as well, but fitting them out just means becoming blind to impulsive, like gravitational waves, which we'd like to be agnostic about. There are some ways of discriminating these in TDI with this Sagnac variable. There are differences between a force on a test mass and the actual deformation you get from a gravitational wave that we need to work on. We would like to eliminate these, or at least be able to discriminate these at instrument level. This is something we're working on now. Final aspect of LISA is that this is very new data as far as data analysis is concerned. All of our sources are on all the time, which means tens of thousands of, in principle, resolvable galactic binaries, in addition to the various supermassive black hole mergers, these extreme mass in spirals. So this demands a very collective approach, a sort of a global fit technique for making all these signals unambiguously separated and to extract parameters from these. So it's a very different scenario. You can imagine this is also, we want to do some of this fairly fast, so we can get out alerts to the astronomy community. We'll be dealing with data which have some interruptions for spacecraft operations with instrument artifacts. This is an extremely rich data analysis problem, which is just getting, well, it's been going for some time, but it's not too late to contribute. There's a website here for the LISA Data Challenge. I won't go into more detail just because of time, but this is, I think, a very interesting data analysis question. And my very last thing on LISA is just, so maybe this is offensive or at least inappropriate for a general relativity audience, but these are what we call sort of simple little engineering details, which are the kinds of things that can sink otherwise beautiful missions that we need to get right. So just to give a couple examples of the things which are being studied in industry now, one of them is releasing the test mass. You have to hold this during launch and then release it into free fall in orbit. Another thing is that the satellites actually have to find each other. This is called constellation acquisition, where you have a microradian or several microradian beam, pencil beam, with which you have to seek out a satellite 2.5 million kilometers away. So this is basically my conclusions. In 2015, 2016, we had the first detections of gravitational waves. We had the LISA Pathfinder launch, which showed that much of the LISA metrology we could do. In 2017, we proposed this to ESA, and it was accepted. ESA did an internal study, and then last year, about a year ago, started what's called the Phase A, which is a competitive study at the industrial level, at the mission level. And we put together our consortium to work on the instrument side. So right now, and if you please can forgive us for being slightly distracted this week, we're right in the middle of what's called the mission consolidation review, which is sort of a midterm review. And the question is, do we have a baseline mission? This is what we're working on now. The launch date is 2034, which would mean gravitational wave science just a couple years after that. ESA is exploring a budget increase with the member states, which would be aimed at possibly advancing this launch date, but I think more generally guaranteeing that we can do both LISA and Athena starting in the early 2030s, that we can guarantee a substantial overlap in their science observation time, and that these will deliver the revolutionary science that we think that they can. So thank you very much. I think I went a couple minutes too long. Sorry about that. Thank you.
Thank you very much. Very nice talk. Questions or comments? Just one here.
You showed the acceleration noise of the LISA Pathfinder is 10 times or something like that better than the spec value. This is very nice, but I want to ask, what is the reason of this difference? Why this is different from the spec value?
Okay, I think the question is, why is your noise model not complete? Is that correct?
Probably.
Yes. So, okay. This is a very important question. Why is it not complete? If I knew it would be complete. So we have other possible candidates that we're considering. We certainly haven't thrown in the towel. Okay. So what you see in the black curve here is what we're sure exists. These were characterized and modeled by dedicated experiments, and so we can quantitatively say that that noise would be present. There are other noise sources which are not on here, several possible gravitational effects, electrostatic effects, magnetic effects, which we can't prove exist at a relevant level here. So we don't explain all our noise. We think we understand it quite well in the millihertz frequency band. The difference between what we explain and what we observe is well below what we need to do on LISA. However, this has to be our extremely high priority is trying to understand this. So there are possible ideas that we're working on. We don't have the smoking gun yet, but we will not stop. We have to investigate any, let's say, plausible or even slightly implausible idea which could explain this, so that we can properly design for this in LISA. The other thing in LISA is we're designing around this system, trying to reproduce the environment as good or better than what we had on LISA.
Thank you.
Thank you.
Is there any other question?
Hi, thanks for the talk. How do you choose the mass of the test mass?
Yeah, okay. Okay, so the test mass is a cube. It's 46 millimeters on a side, about 2 inches. It's made of gold platinum, which was the most expensive, but also the most heavy and magnetically pure system that we could find. You can make combining the paramagnetic and diamagnetic elements, you can make a very high, very low magnetic susceptibility and very clean as far as magnetic inclusions. The other thing is going as heavy as possible. You're dividing out surface forces by as large a mass as possible to get to a smaller acceleration. Why did you stop at 2 kilograms? Maybe this is also, so okay, the bigger the mass you go to, so our really dominant or most frightening surface effects are the Brownian noise, the electrostatic force noise. These get better in terms of acceleration noise the heavier the mass and also the bigger the mass, because you're averaging out over a larger surface area. 2 kilograms was about the biggest that we thought we could launch without sort of exploding the launch mass of the entire system. Another thing that I can say on top of this is that, okay, you have to hold the test mass during launch. The larger the test mass is, the bigger that system has to be. The bigger that system has to be, the bigger the fingers which are going into so this electrostatic sensor around the test mass is a Faraday cage, which is shielding us out from electrostatic effects. The heavier the mass, the bigger the system you need, the larger the holes are in this Faraday cage, and also the bigger the system is. So, back when we decided this, our evidence, I have to admit, was relatively weak that this was big enough. It is big enough. I mean, we showed this with LISA Pathfinder. We did measurements with a torsion pendulum where you have a hollow test mass, which got us down to something like tens of femtonewtons. And that's for most surface forces. We had an idea that these were small enough to not be a real showstopper. And then the full test came with LISA Pathfinder. If we could launch, 10 kilogram test masses with several centimeters gaps around it, we would be even happier, but we need to find someone with a launcher and the money to do that. So that's sort of the trade-off there. We thought this was, our experimental knowledge was that this was good enough to do LISA sensitivity, and we showed that it is.
We have time just for one quick question. Okay, if there is nothing, let's thank the speaker again.